out. There we go. So chemistry 111, this is where we left off. Last class was with example 7.11, and we didn't solve this problem. And I told you to take a look at this one and the remaining problems in this chapter before we came to class tonight. So it says, what is the maximum number of electrons that could be present when we have a principal quantum number, which is 3? So when we have a principal level for which n is equal to 3, what's the total number of electrons that we could have there? Well, if we think about it in terms of our principal quantum numbers, N, L, ML, and MS, if n is equal to 3, when we have that level, when n is equal to 3, what are the possible values of L? L could be 0, 1, or 2, right? Because L can be 0 all the way up to n minus 1. So those are our 3 possible values of L. Now, for each one of these, if I have L is equal to 0, what are my possible values of ML? The only possible value for ML that I have is 0. And so since there's only one kind of orbital when my L is equal to 0, which is an s orbital, right? That's an s orbital. I can only have a maximum of 2 electrons because I've only got one orbital. So this represents, remember, ML is the number of orbitals or the direction of the orbitals, okay? So if I have 2 electrons in every orbital, and we can put that here, 2 electrons in each orbital, since I have an s orbital, right? L is equal to 0, that's an s orbital. Okay, just a little review here. When L is equal to 0, 1, 2, 3, that's an s, p, d, or an f orbital. So when I have an s orbital, there's only one type of orbital, one direction, and so that can hold 2 electrons. If you're not 100% sure about what I mean by that, let's try it for L is equal to 1. When I have an L equal to 1, and I'm going through all the possible values of L, what are the possible values of ML? The values I can have are -1, 0, and +1, and I can put 2 electrons in each one of those 3 orbitals, right? There are 3 orbitals. So 2 times 3 gives me a total of 6 electrons. And when I have L is equal to 2, well, my values of ML are going to be -2, -1, 0, +1, and +2. That's a total of 5 orbitals. That's a total of 5 orbitals. 5 times 2 gives me 10 electrons. So if I tally all that up, 2 plus 6 plus 10 gives me a total of 18 total electrons. Again, if you're like, why can you put 2 electrons in each orbital, right? Why can I put 2 electrons in each orbital? It's because in each orbital, and we practiced drawing some orbitals last class, we said there's one with an upward spin and one with a down spin, right? We have an MS value that can be +0.5 or -0.5, right? That's what these arrows represent. One of them pointing up represents +0.5, and the other one pointing down represents -0.5. So that is a mantra you want to have throughout your electron configuration. Every orbital can hold a maximum of 2 electrons. Now, if you took the time to read our textbook, which I'm sure you did, I'm sure you were sitting around reading it with bated breath, there is a faster way to determine the total number of electrons you can have at a certain principal level or a certain principal quantum number. And I'm just going to go over that quickly because I've taught the class enough to know that students don't use it a lot, but the rule is maximum number of electrons is going to be equal to 2 times n squared. So if your n is equal to 3, you have 2 times 3 squared. 3 squared is 9. 2 times 9 is 18 electrons. Now, again, that's a shorthand. Okay, that's a shorthand. If you can memorize that, no problem. Be my guest, okay? But personally, I find the longer way actually a little bit easier to tally up the total number of electrons you can have when you have a principal quantum number of 3. If you want me to show you another way to think about this, and this is going to kind of tie in with our electron configuration, if we go right back towards the beginning, when I was talking about the periodic table, I'm trying to find the periodic table I looked at last class. So if we delete all the spinach that I have on here just to make life a little easier, okay, if we delete all this, look, how many electrons can we have in with a principal quantum number of 3? We have n is equal to 1, n is equal to 2, n is equal to 3. Okay, well, how many total groups are there in the periodic table? I told you to bring a periodic table with you this evening. This periodic table is not divided up into all the groups, but there's a total of 18, right? We go from group 1 all the way to 18, and that's using the Arabic number convention. Yes, I know there's 1A, 2A, and then 3A to 8A, so on and so forth, and there's the B ones, okay? But there's a total of 18 groups. So look, that means that when I have 3, a principal quantum number of 3, I can have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Ugh, I knew I was going to mess it up. So I can have a total of 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So there's a total of 8 possible electrons that you can have when you have a principal quantum number of 3. And how many types of L's are there when you have a principal quantum number of 3? When n is equal to 3, the values of L can be 0, 1, and 2, an S, a P, and a d orbital. Well, looky, a 3s, a 3p, and a 3d. So it all comes together in the end. All right, let's take a look at question 7.12, which also deals with quantum numbers. It says an oxygen atom has a total of 8 electrons. If you look at the periodic table, you'll see that oxygen is in the second period. It's element number 8. It's right between nitrogen and fluorine, and it has an atomic number of 8. That means it's got 8 protons in the nucleus, and if it's neutral, it's got a total of 8 electrons, doesn't it? It says, write the 4 quantum numbers for each of the 8 electrons in the ground state. Well, let's start. If I look at where the electrons are for the oxygen atom, okay, and I'm going to go all the way back to that periodic table again, which is just super duper handy when you're doing this. So I'm going to delete all this stuff again. And now we're just going to focus on oxygen. So we're going to delete this. And we'll delete this too. All right, there we go. So where is oxygen? Look, if I fill this in, we've got hydrogen here. We've got helium here. We've got lithium. Then we have beryllium. Now we have one. So we have boron, carbon, nitrogen. So I'm going to try to divide this up as best I can. So we have boron, carbon, nitrogen, oxygen, fluorine, and neon. There, that's my best I can do. So again, look, we have 1, 2, 3, 4, 5, 6, 7, 8 electrons. Where are those electrons found? They're found when you have a principal quantum number n is equal to 1, and they're found when you have a principal quantum number n is equal to 2. So those are the only 2 possible values for my principal quantum number. N is equal to 1 and n is equal to 2. And I'm going to have a total of 8 electrons. So let's go back and start working on them. We can only have an n equal to 1 and put it like this, and n is equal to 2, and I've got a total of 8 electrons. Now remember, according to the Aufbau principle, we're going to start with the lowest energy electron. So that means we're going to start with n is equal to 1. Let's do that. If I fill out n, L, ml, and ms for n is equal to 1, okay, what's the only possible value for L? 0. What's the only possible value for ml? 0. What's my possible value of ms? Well, I can have plus a half, and I could also have the same NL and ML, and I could have minus a half. Now remember, the maximum number of electrons I can have when I have an n is equal to 1 is 2 times n squared, which is 2 times 1 squared, which is 2 times 1, which equals 2 electrons. These 2 represent a total of 2 electrons. So that means I'm done with my n is equal to 1. Now I have to move on to n is equal to 2. Let's do that. Let's start like this. We know that when n is equal to 2, what are my possible values of L? Okay, here my only possible value of L was 0, but now my possible values of L are 0 and 1. Okay, so we'll start with 0 because that's the lowest energy. So we'll start with 0, 0 plus a half, and 2, 0, 0 minus a half. And if you're wondering, what are you doing? I'm just building up an energy, right? I have to start with n is equal to 1. And remember that I told you that L is equal to 0, 1, 2, 3, S, P, D, F. And I told you that S is lower energy than a P, which is lower energy than an F, or D than an F. So that's why I started with S orbitals and then S orbitals here. Right, now that I've filled up the S orbital, now I'm going to move on to a P orbital, which can hold more electrons. So essentially what I've done so far is I've filled up the 1s electrons and I've filled up the 2s electrons. Now I'm going to move on. I've covered a total of 4 electrons, right? 1, 2, 3, 4. I've got 4 more to go. I haven't finished all the possible electrons I can have when n is equal to 2, right? Because when n is equal to 2, the total number of electrons I can have when n is equal to 2 is 2 times 2 squared, which is 8. So that means when I have a principal quantum number of 2, I can hold a maximum of 8. So I've got more than enough room. Let's continue. So what if I have a 2, and now I have an L is equal to 1? Well, remember when L is equal to 1, my possible values of ML rather are -1, 0, and +1. So I'm going to do that -1, 0, and +1. I'm going to say that all of these are +0.5, +0.5, and +0.5, like that. And again, these are 2p electrons, but I've only got 7. I've got 1 more to go. I'm kind of running out of space here. I wanted to put them all vertically, but I have 1 more, and I'm going to have to put it up here. I'm going to have 1 more principal quantum number where I have a 2, I have a 1, I have a -1, but now I'm going to have to start pairing them up, aren't I? I'm going to have a -0.5, like that. Okay? What I'm doing is, remember that when you have a 1s orbital, there's only one type of s orbital, right? It's going to hold 2 electrons. 1, 2. That's represented by these 2 sets of quantum numbers here. When I have a 2s orbital, there's only one type of s orbital, right? You can't move a sphere in any other direction. So I have 1, 2 electrons here. And then for the p, there are 3 types of orbitals. Okay, we'll call these 2p. You could say 2px, 2py, 2pz. I'll make it simpler and just say all 3 of these are 2p orbitals. Remember, according to Hund's rule, you've got to have the maximum number of unpaired spins. So we start +0.5, +0.5, +0.5, and -0.5 or -0.5, like that. And that's the electron configuration of oxygen. And that shows you all of the quantum numbers for the 8 electrons in oxygen. What we're going to do later on tonight is we're going to look more at electron configuration. And once you really get you start to be confident in electron configuration, it clears up quantum numbers even more, I find, for students. So if you're wondering about this electron configuration that I have in the yellow box, I have 1s2, 2s2, 2p4. You can actually write that out like this. You can just say 1s2, 2s2, 2p4. And now you know what those superscripts mean. The 2 electrons are the 2 electrons with opposite spins in the 1s orbital. These 2 electrons are the 2 electrons with opposite spins in the 2s orbital. And these are the 4 electrons in the p orbitals. This is a table which is really small, but if we zoom in on it, and this comes from your textbook, you see that for oxygen, the electron configuration, well, what we had written was 1s2, 2s2, 2p4, but you see that the end of it is identical to what we wrote, okay? 8 electrons. And if you're wondering, what the heck is this here? Why does it say helium before it? I'm going to get to that in a second, okay? I'll explain to you where that comes from, but it's basically a shorthand. It's a faster way of writing out the electron configuration. So hopefully what I was planning on kind of with this presentation or with my slides is that it hopefully would all come together, because I started out with this slide during last lecture on Tuesday, and I said this is what we're going to use to do all of our electron configurations, okay? So it doesn't matter what element you have on the periodic table, you're always going to follow this order. You're going to go from a 1s to a 2s, then you go to a 2p, then you go to a 3s, to a 3p, to a 4s, to a 3d, to a 4p, to a 5s, to a 4d, to a 5p, so on and so forth. So I told you that you are going to have to be able to follow this, okay? We go from a 6s actually down to a 4f, and then back up to a 5d, and back up to a 6p, and we'll get some practice on this, okay? So again, this is what I was trying to do, is tie it all back together to that first slide. So with that in mind, let's see if we can write out an electron configuration for sulfur. You could just go back on this slide and look it up and say, well, I'll just find sulfur, there it is. But let me show you how to do it a lot faster. And I'm going to have to go over to a periodic table, so just bear with me for a second. So we're going to do sulfur and palladium are the two we're going to do. Just give me 2 shakes of a lamb's tail here, because I put some periodic tables, or at least I thought I had. Come on. There we go. So here's a periodic table that we can work off of. So again, we're going to start with sulfur, okay? Sulfur is right here. It's element number 16 on the periodic table. Remember, we have a principal quantum number. N is equal to 1, N is equal to 2, N is equal to 3. Yes, I know here it goes down to 4, but we're not even going to get that far. So how are we going to start? We've got 1, 2. So that means we've got 1s2. Now the s's are all done. If you're thinking, hey, Mr. Dion, wouldn't every element past helium start out with 1s2? Yes, absolutely. Now we're going to go to 2s, or to 2. So we have 2s1, 2s2. So that's 2s2. Remember that these two groups are the s block. Now, if you're like, Mr. Dion, you messed it up from the very beginning because you said that helium is in an s orbital. If you look around the internet, sometimes you'll actually find periodic tables that have helium listed over here. Okay, they actually put helium there because helium's electrons are both in an s orbital. The reason most periodic tables put it over here, helium over here, even though the electrons are in an s orbital, and this is the p block over here, the reason why is because both of helium's electrons are paired up. Everything's paired up, which causes it to be inert or unreactive. So that's why they slap it over here with all these elements, which are known as the noble gases, which are unreactive. Okay, so that covers that exception. Then from there, we move on to the p block. So we have 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. So we've got 2p6. Now we've got a total of 10 electrons, right? We've got 2 plus 2 plus 6, so we've got 10. But sulfur has 16 electrons. We're not done, so let's keep going. Now we're going to go down here. We've got 3s1, 3s2. So 3s2. We come back over here. We've got 3p1, 3p2, 3p3, 3p4. And there you go. We have 3p4, and that is the electron configuration of sulfur. 1s2, 2s2, 2p6, 3s2, 3p4, and that is sulfur. Give me a thumbs up if you follow me on that a little bit. If you're like, I think I could do that, you know, give me a little time to practice. Or stop me if you have a question about what I'm doing. Feel free to interrupt me at any point. Just say, Mr. Dion, I don't understand, or could you repeat that or something? So now I'm going to copy this, what we just did. I'm going to take that out of here. And we're going to go back to our original slides here, right down here, and we're going to paste those in. I'm going to paste that in. And if you go back to what I had here, you'll see that for sulfur, it's different, right? It says neon, and then it says 3s2, 3p4. If we go back to our answer, you see that our answer ended up with 3s2, 3p4. So if you're wondering, what is that electron configuration that's in that table? What they do is they take any electron below the electrons with the highest principal quantum number, right? The highest principal quantum number in sulfur is n is equal to 3. So they take all of these electrons and they make a shorthand. If you look at 1s2, which gets you to helium, 2s2, which gets you to beryllium, but then 2p6, can anybody tell me what element has a total of 10 electrons in it? And it's not a trick question. Thanks, Christian. Thanks, Anthony. It's neon. And so the shorthand version, so this is the full version here, but the shorthand version is to take all of those electrons below the highest principal quantum number, and we call these core electrons, and just to put the noble gas that has that electron configuration, which is neon. Neon is 1s2, 2s2, 2p6. So we shorthand it, we put neon, and then we put 3s2, 3p4. Now you might think, well, it's not saving me that much, time. I mean, come on, I could write that out pretty quickly. Well, yeah, you're right. Once you get to some of these elements here, you get to elements with really big atomic numbers, you save a lot of time by putting the noble gas that precedes it. And you'll notice that every one of these shorthands, look at all the elements that are in brackets. They're only noble gases. Okay? So we go with the noble gas that precedes the element, or comes before it. We put it in square brackets, and that's our shorthand. And if you're wondering, do I have to know both? Of course. Of course you have to know both. Okay, let's try palladium. Palladium is element number 46. I'm going to go back from whence I came, which was over here where I had that nifty periodic table. So we're going to do palladium. Just bear with me here. I'm going to erase some of this spinach, and I'm going to go a little faster this time because I'm going to assume that you're following me along here with some of the concepts. There we go. So palladium is over here. It's element number 46. So we're going to start out with, we need a total of 46 electrons. Is it just me, Jerry, or is that a lot of electrons? That's a lot of electrons, right? So 1s2, 2s2. Now we've gotten these ones. Now, next we've got 2p6. 2p6. We're still not there. Let's continue on in our journey. 3s2. 3s2. 3p6. 3p6. Still not there. 4s2. 4s2. Remember that here it drops down to 3d, right? It goes from 1, so this is n is equal to 1, n is equal to 2, 3, 4, 5, right? But it drops down here with the transition metals. So we have 3d, and how many d electrons are there? If you count up, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Does that make sense? Well, when L is equal to 2, that's a d orbital, and your mLs would be -2, -1, 0, +1, and +2. Each one of these orbitals can hold 2 electrons. 5 times 2 is 10. Makes perfect sense. So we have 3d10. So we've got all those. Next, we go back up to 4 again. We have 4p6. 4p6. Then we have 5s2. 5s2. Then we go down to the 4ds. And we have 4d1, 4d2, 4d3, 4d4, 4d5, 4d6, 4d7, 4d8. Not 48, 4d8. Like that. Okay, so let's copy all that spinach. It's not going to be easy to do, is it? Take all that. And we're going to copy it. We're going to put it back in here. There we go. Now let's go up to this table and let's find palladium, which again is element number 46. So it's up here. And they have 4d10. Let's go back here. And let me show you something. So we don't have 4d10, do we? Well, if we look at all of the electrons that are covered by the noble gas that precedes palladium, if you look at the periodic table, the noble gas that comes before palladium is krypton. So we could shorthand this as krypton, and krypton is covered by all of this, all the way up to 4p6. Krypton 5s2, 4d8, like that. If we draw out the orbitals for that, let me show you what it would look like. Let me fix this, 4d8. We have our 5s orbitals, there's only one of those, and we have our 4d orbitals, and there's 1, 2, 3, 4, 5 of those. Look what happens. You have 1, 2, and 1, 2, 3, 4, 5, 6, 7, 8. So here's an interesting rule, is that if I had written the electron configuration out this way, I have 2 unpaired electrons. And so atoms are going to be more stable when all of their electrons are paired up. So palladium is kind of an exception in that what it'll do is it'll take both of the electrons from the 5s orbital and it moves them up into d orbitals so that you end up with nothing in the 5s and you have the 4d, you have it completely full. Okay, just because it's more stable. So you can write that down. It's more stable. And that's why the actual configuration that you see is krypton 4d10. There are other exceptions in the periodic table. Okay, there are other electron configuration exceptions, and I want to take a look at some of those with you this evening. But before we do that, I wanted to spend some time looking at some practice problems with you. Who's up for some practice problems? Anybody? Maybe yeah, maybe no. Sorry, I'm just trying to get organized here. I kind of made a mess on my desk. Put that over there. Okay, all right. We got 3 people who are down with doing some practice problems. So I'm just going to go through some of the practice problems that I had picked from our textbook. Just give me a second. I had put the numbers up here on my computer somewhere, and my computer's being a jerk. There we go. I don't need that. Sorry, my computer's really a piece of junk these days. So the question I want to start looking at, and I have to get my textbook out, is 7.7a. So this is, of course, chapter 7. And we're going to do some practice problems for a little bit. It's only 5:30. We got some time. And then we'll take a look at some chapter 8 material after that. Okay, so question 7.7a. And you're going to need a calculator. So if you don't have a calculator, get one out to check my math, because I make all kinds of mistakes like anybody else. 7.7a asks us, what is the wavelength of light having a frequency of 8.6 times 10 to the power of 13 hertz? So if we have a frequency of light, which is equal to 8.6 times 10 to the power of 13 hertz, it says, what is wavelength? Well, remember that the speed of light, whether it's visible light or any other kind of electromagnetic radiation, X-rays, gamma rays, infrared, microwaves, UV, IR, right? Radio waves, they all have the same speed that we call c. And c is approximately equal to 3.00 times 10 to the power of 8 meters per second. And we can use the formula that the speed of light is equal to wavelength times frequency in order for us to solve for wavelength, because we can rearrange that as wavelength is equal to c over frequency. Now, if you look at the units of c, which are meters per second, and you divide them by frequency, which is in hertz, that doesn't look like a wavelength, does it? But remember that a hertz is the same thing as a second to the power of -1, or a reciprocal second. So in other words, we can say that this is equal to meters per second. So these cancel out. If you're unsure about that, if you're unsure about why that is, well, remember that meters per second up here is the same thing as saying meters times seconds to the -1, okay, divided by seconds to the -1, okay? So I meant to put seconds to the -1. So seconds to the -1. So you can see that they cancel out, and you're going to end up with meters. And so when we plug our numbers in, our wavelength is going to be equal to 3.00 times 10 to the power of 8 meters per second divided by 8.6 times 10 to the power of 13 seconds to the -1. Again, I just showed you how these are going to cancel out, and we're going to end up with our wavelength in meters. Now I'm going to double check my math here. Let's see here. So I have 3 times 10 to the power of 8 divided by 8.6 times 10 to the power of 13. and I end up with a number which is, no, that's not right. So I have 3 times 10 to the power of 8 divided by 8.6 times 10 to the power of 15. That's more like it. I end up with, and I should only have 2 sig figs, 3.5 times 10 to the negative 6 meters. So that is my wavelength. Now, notice that you should be able to, convert meters into nanometers, which are commonly used to measure wavelengths of light. So how would you do that? Well, if I have 3.5 times 10 to the negative 6 meters, you should know that in 1 meter you have 1 times 10 to the negative 9 nanometers, right? Nano, 9. So you take that number, you multiply by 1 times 10 to the negative 9. What am I doing wrong here? Sorry, I'm wrong here. I meant to say in 1 nanometer, you have 1, there we go, that's better, 1 times 10 to the negative 9 meters. So we take 3.5 times 10 to the negative 6, and we divide it by 1 times 10 to the negative 9, and you end up with 3.5 times 10 to the power of 3, so you end up with 3.5 times 10 to the power of 3 nanometers, which is 3,500 nanometers. Give me a thumbs up if you think you could solve for wavelength given frequency using this formula right here. So this is just an application of this formula, nothing more than that. All right, good, awesome. Let's try another one. I'm going to go a little faster here. Question 7.7b. So this is 7.7b. It says, what is the frequency in hertz of light having a wavelength of 566 nanometers? So now we're looking for frequency, and we know our formula that C is equal to wavelength times frequency. So we can solve that for frequency. Frequency is going to be equal to C divided by wavelength. We have our C, which is 3.00 times 10 to the power of 8 meters per second. They told us that our wavelength is equal to 566 nanometers, which is the same thing as saying 566 times 10 to the negative 9 meters, like that. So we're going to put that in our denominator. So we've got 566 times 10 to the negative 9 meters. Meters cancel out. So we take 3 times 10 to the power of 8 divided by 566 times 10 to the power of negative 9. And we end up with 5.30 times 10 to the power of 14 seconds to the minus 1. Remember that a seconds to the minus 1 is the same thing as a hertz. So we have 5.30 times 10 to the power of 14 hertz, just like that. Okay, let's move on from there. Let's try question 7.16. So if you have your book, we're going to go over to question 7.16 from our textbook. It says the blue color of the sky results from the scattering of sunlight by air molecules. The blue light has a frequency. So they've given us the frequency, nu, which is 7.5 times 10 to the power of 14 hertz. And it says, A, calculate the wavelength in nanometers. And then it asks us to calculate the energy in joules of a single photon associated with this frequency. So let's start out by calculating the wavelength using our formula. C is equal to lambda, wavelength, times nu, which is frequency, right? This is nu. It's just a Greek letter, nu. This is lambda, which is another Greek letter. So that's what I'm saying is lambda times nu. And we want to solve for the wavelength. Wavelength is going to be equal to C over nu. We have our speed of light, 3.00 times 10 to the power of 8 meters per second. We divide that by the frequency. Remember, this is the same thing as a second to the minus 1. So we've got 7.5 times 10 to the power of 14 seconds to the minus 1. Those cancel, and I'm going to end up with my wavelength in meters, and my wavelength is going to be, I should only have 2 sig figs because I have 2 sig figs here, and I'm using 3 sig figs in my speed of light. Therefore, I end up with 4.0 times 10 to the negative 7 meters. Like that. That's my wavelength. If you want to convert that into nanometers, you're going to divide by 1 times 10 to the negative 9. So this is supposed to be a 4, isn't it? Clean that up. So there we go. There's our 4. So again, in 1 nanometer, we have 1 times 10 to the negative 9 meters. So you could do that conversion, and you end up with a wavelength that is equal to 4.0 times 10 to the power of 2, or 400 nanometers. Okay, the next part of 7.16, so part B, asks us about energy. Energy. How do we figure out the energy of a photon? Well, you probably would have noticed this formula from my introduction video, 7.1 through 7.4 on YouTube. And there's a couple of formulas that were in there, right? You saw the formula that E is equal to h nu, which was discovered by Max Planck when he was trying to explain the energy emitted by what's called black body radiation when he heated up solids, and he was trying to correlate the amount of energy given off to the frequency of light that was given off by objects that were heated up. So h is Planck's constant, and nu is our frequency. Now, Planck's constant is a constant, and I will give you that constant on your exam. It is 6.63 or 6.626 times 10 to the negative 34 joules times seconds. And then if I multiply that by the frequency that I got from the get-go, which is 7.5 times 10 to the power of 14 seconds to the minus 1, you see that the seconds and seconds to the minus 1 cancel, and I'm left over with units of energy in joules. And when you do that, you get the energy is equal to 5.0 times 10 to the negative 19 joules. Now remember, that's a small amount of energy, but this is for one photon only. This is only for one photon. And we know that when we shine a beam of light, that it's comprised of particles that we call photons, right? That was discovered by Albert Einstein when he discovered the photoelectric effect, right? He bombarded metal with light and it knocked electrons loose, which didn't make any sense because people thought that light was just a wave. How can a wave knock an electron loose from a solid? So that is how Albert Einstein discovered that light not only has wave properties, but it also has particle properties. All right, let's move on from that one. That's 7.16. Let's see here. Let's take a look at. Let me see here. Yeah, let's talk a little more about the photoelectric effect, which I think I told you last class that that is what Albert Einstein won the Nobel Prize for. A lot of people think that it's for E equals mc squared, and it is not for that. He actually won the Nobel Prize for the photoelectric effect. So let's try a question that deals with the photoelectric effect. I think I went over a question or two like this in my videos, but this is a good one. It says, if you have light that has a frequency of 2.11 times 10 to the power of 15 seconds to the minus 1, which is, again, the same thing as a hertz. So if you have light at that frequency and you shine it on the surface of gold metal, the kinetic energy of the electrons is found to be 5.83 times 10 to the negative 19 joules. So I'm going to write that down, that kinetic energy is equal to 5.83 times 10 to the negative 19 times 10 to the negative 19 joules. That's the amount of kinetic energy that the electrons have that are knocked off of the metal. And it's asking us, what is the work function of gold? Okay, what is the work function? So W is equal to what? Remember that work function is it's basically the strength with which the electrons are held by the metal, right? It's the amount of energy that it would take, or the minimum amount of energy is what I'm looking for. It's the minimum amount of energy that would be required to remove an electron from the metal. Let's think about it another way. When we shine light, which has energy, at a metal, and this is again based on the photoelectric effect, the amount of energy is going to be equal to the kinetic energy of the electron that's ejected plus the work function. Remember that that work function is just the minimum amount of energy required to remove the electron, right? But if you've got anything beyond that, if you have any more energy than that, then the electrons that are ejected are also going to have some kinetic energy associated with them. And so we can rearrange this formula to solve for W, can't we? We can say that W is going to be equal to E minus the kinetic energy. Now you might be wondering, well, I've got the kinetic energy. Where am I going to get E from? Well, remember that E was equal to Planck's constant times the frequency. And we have the frequency of the light. So we can rewrite this as E is equal to h nu subtract Ke. Let's give it a try and see if we get some kind of answer that makes sense. So our h nu, our energy, is going to be Planck's constant, 6.63 times 10 to the negative 34, oops, getting ahead of myself, joules times seconds, multiplied by the frequency, 2.11 times 10 to the power of 15 seconds to the minus 1. Subtract the kinetic energy, which was 5.83 times 10 to the negative 19 joules. Well, this looks pretty good to me because here I have joules, and when my seconds cancel out, I end up with joules here. So joules and joules are compatible, and they make sense because the work function is a certain amount of energy. It's the minimum amount of energy that's required to remove an electron from the metal. Well, now it's just a matter of plugging the numbers into your calculator and solving, for the final answer. So I reduced this to 1.40 times 10 to the power of negative 18 joules, subtract 0.583 times 10 to the negative 18 joules. And if you're wondering, Mr. Dion, why in the heck did you change this from, 10 to the negative 19 to 10 to the negative 18? Why did you move the decimal place over here? The reason why is because it's a lot easier to just do the math in your head if you do it this way. Okay, because remember, now that both of these exponents are the same, you can just take 1.40 in your head and subtract, 0.58 from it, which would give you 0.82. So it would actually give you 0.82 times 10 to the negative 18 joules, but you want to write it out in proper scientific notation. So the mantissa should always lead with a number, so you just change it to 8.2 times 10 to the negative 19 joules, like that. There's nobody who's hearing the sound of my voice who can't add and subtract numbers, right? Everybody who's taking this class can add and subtract numbers, especially when you have a calculator in your hand, right? Anybody can do that. What's difficult about chemistry is reading the problem and interpreting what the heck is going on. So again, what happened was Albert Einstein shown, and this is Mr. Dion's representation here, okay? He took a piece of metal under glass and he shone a beam of light at it. And what it did is that it knocked electrons loose from the metal. And the minimum amount of energy that's required to knock the electrons loose from the metal is called the work function. But if you give them more energy than the work function, they also come off and they've got a little bit of speed too, don't they? They got a little bit of energy, to make them move even faster. And that is the excess energy. So that's where we get this formula here, that energy is equal to the work function plus the amount of kinetic energy that the electron has. So again, photoelectric effect, if you're unsure about where this question came from or what it's based on or anything like that. Let's take a look at question 7.30. This deals with one of the most important formulas that you're going to see at the beginning of chapter 7. It says the first line of the Balmer series occurs at a wavelength. So we've got a wavelength, I like to write things down, of 656.3 nanometers. What is the energy difference between the two energy levels involved in the emission that results in this spectral line. So basically, we want to find the energy associated with this wavelength. But so far, the only formula that we looked at for energy was energy is equal to h, Planck's constant, multiplied by nu. That doesn't get us very far, does it, if we want to calculate the energy associated with this wavelength, right? Because there's always a certain amount of energy associated with any wavelength of electromagnetic radiation. Before we move on, I have a quick question for you guys. Who's been reading chapter 7 and kind of paying attention to what's going on? What would have more energy? A wavelength of light with a short wavelength or a long wavelength? Which one would have more energy? Long wavelength of light or a short wavelength of light? Yeah, a short wavelength of light is going to be higher energy. A long wavelength of light is low energy. Now, how do I know that? Because if I use this formula that C is equal to lambda over or times nu, which we looked at several times this evening, I can solve that for nu, can I? I get that nu is equal to C over lambda. We also use that. And now I can plug this into this part of my equation, and I get that E is equal to H times C over lambda. So we see that energy and wavelength are inversely proportional. That means when energy is big, wavelength is small, right? So that's why Branson said a short wavelength or a small wavelength, whatever you want to call it, is going to result in higher energy. Conversely, if you look at the relationship between energy of electromagnetic radiation and frequency, they're directly proportional. The higher the frequency, the higher the energy. Let me show you a way that my colleague explained this to me, okay? We know that frequency is the number of cycles of electromagnetic radiation per second. Well, you saw how many cycles I drew there with that frequency that I was moving my pen at. What if I move my pen at a higher frequency for the same amount of time? Okay, that looks like crap. But which one looks like it took more energy? The one that I just drew took a lot more energy than the first one that I drew, right? Think about it. Long or okay, like that. So if we have a low frequency, low numbers of cycles per second, that's low energy. And if we have a high frequency, a high number of cycles per second, then it's going to be high energy. Anyhow, I hope that made some sense to you. But now we can plug some numbers into our equation. We can say that energy is equal to Planck's constant, 6.626 or 6.63 times 10 to the negative 34 joules times seconds, multiplied by the speed of light, 2.00 times 10 to the power of 8 meters per second. All of that divided by my wavelength. Now my wavelength is in nanometers, and I'm going to need it in meters, won't I? But we said that this is the same thing. 1 nanometer is the same thing as 1 times 10 to the negative 9 meters. So we can just change this to 656.3 times 10 to the negative 9 meters. And look at this, it's not magic. Meters cancel and seconds cancel, and we're left over with units of joules. So that when we plug that all into our calculator, we end up with an energy of 3.03 times 10 to the negative 19 joules. Is this helping anyone? If not, we can move on to chapter 8, but if you guys want to keep doing some review, I'm happy to look at some more problems. You can turn this into a democracy, whatever you guys want to do. Do you want to look at some more problems? Yes, or do you want to move on to chapter 8? And I'm good with either one. Maybe we should look at a couple more problems. Let's take a look at a problem that deals with emission. Okay, let's try question 7.32. And this one is just kind of another, Kristen, all right, good. It says here, question 7.32 asks us, and this, I guarantee you I'm going to ask you a question like this on your practice exam and on your actual exam. It's a classic. It says, calculate the frequency and wavelength of the emitted photon when an electron drops from n is equal to 4 to n is equal to 2 in a hydrogen atom. So that means our n initial, where it starts, is 4, and our n final, where it ends up, is 2. And we want to calculate the frequency and wavelength. Well, the formula that we can use, because we're looking for frequency and we're looking for wavelength, the formula that we're given is that the energy, or the change in energy, due to this transition dropping from n is equal to 4 all the way down to n is equal to 2, right? When the electron, when it drops from a high level to a low level, it's going to emit a photon of light. So what's the energy associated with that photon? Well, we have the Rydberg constant, RH, multiplied by 1 over n initial squared, subtract 1 over n final squared. So it's really nothing more than a matter of plugging the numbers into the equation. But I want to talk to you about the sign, because if you look up the Rydberg constant, which I don't know what page it's on in your book. It's probably a different page than mine. I'm just looking at my textbook here. Boop, boop, boop. Yeah, you guys, if you bought the textbook from the college, it might be on a different page. Dun, dun, dun. Just trying to see where I put it. Well, the first time I see it used in the textbook is in example 7.4, which on my book is on page 286. I don't see it listed here before. They might just show it to you in that problem. No, it's on page 284 in my textbook. It says RH, the Rydberg constant for the hydrogen atom, has a value of 2.18 times 10 to the negative 18 joules. So we have 2.18 times 10 to the negative 18 joules. And the sign of that constant, which is positive, has some significance. Let me show you what I mean. When you take 1 over the n initial, which was 4, 1 over 4 squared, subtract 1 over 2 squared, that means you're taking 2.18 times 10 to the negative 18 joules, and you have 1 over 16 subtract 1 over 4. So 1 over 4 is a bigger number than 1 over 16. So you end up with a negative number in that parentheses, don't you? You have 2.18 times 10 to the negative 18 joules multiplied by negative 0.1875 is what I put in here. Again, we can only have 3 sig figs in our final answer, but you calculate the delta E and you get that delta E is a negative number, right? This is a change in energy, and there's significance to the sign. So it's going to be negative 4.09 times 10 to the negative 19 joules. The significance is this, is that when you have a negative sign for your change in energy, this means it's emission, because you're going from a high energy level to a low energy level, and a photon of energy is given off. Now, conversely, if it absorbs energy, and maybe I'll use a different color, if energy was absorbed, can anybody tell me what that situation is called? When you go from a low energy level to a high one, it's not emission. What would that be called? And it's not a trick question. Emission versus the opposite of emission would be? Anybody? No, it's not ionization. It would be absorption, okay? If when delta E is positive, that's due to absorption of energy. When delta E is negative, that's due to the emission of energy. So this formula, all it does is it tells you the change in energy when an electron goes from a low energy level to a high energy level. You'll end up with a delta E that's positive, or when it goes from a high energy level to a low energy level, you end up with a delta E that's negative. There you go. So the formula is really, really handy. I don't know why I can't see what you guys are typing here. Anyhow, all right, let's move on from there. So now it's asked us in 7.32 for 2 things. It asked us for the frequency and the wavelength. Well, to solve for the frequency, I'll just do it over here. We have the E is equal to H times nu. So nu is going to be equal to E over H. We have our energy, which is 4.09 times 10 to the negative 19 joules divided by H, which is 6.63 times 10 to the negative 34 joules times seconds. Joules cancel, and I end up with a frequency that is equal to 6.17 times 10 to the power of 14 hertz. Hertz, like that. Now you might be saying, Mr. Dion, you made a mistake. You forgot the negative sign here. No, I didn't. I know that the delta E is negative. That tells me about the emission, that the energy of the electron is being emitted as it goes from a higher energy level to a lower energy level. But I take the absolute value when I plug it into this equation where I'm solving for frequency, because it wouldn't matter if this quantity of energy came from emission or absorption. It's still going to be associated with the same frequency of light, right? E is equal to h nu. E is equal to h nu. The frequency of light is going to be the same for the absorption or the emission, so it doesn't matter, and there's no such thing as a negative frequency. Now, if we want to solve for wavelength, I'm sure you could probably do that faster than me. We have that C is equal to wavelength times frequency. And sorry, I'm solving for wavelength. The wavelength is equal to C over frequency. We have our speed of light, 3.00 times 10 to the power of 8 meters per second, divided by our frequency, 6.17 times 10 to the power of 14 seconds to the minus 1. These cancel, and we end up with a wavelength that is equal to we end up with a wavelength that is equal to 4.86 times 10 to the negative 7 meters, which if we take that and we say in one nanometer, there's 1 times 10 to the negative 9 nanometers, we end up with 486 nanometers is our wavelength. Give me a thumbs up if you follow me on that one. Classic question, very important question, that you understand the Bohr atom and the equations associated with the Bohr atom. Okay, if you look in the textbook in the back of your book, it says that this question comes from section 7.3 of our textbook. There we go. Let's try one more that deals with that, and then maybe we'll move on from there. Okay, maybe we'll take a short break after that. Let's try one more that deals with those sections. Let's try 7.34, and then we'll take a break. So 7.34 says an electron in the hydrogen atom makes a transition from an energy state of a principal quantum number n initial to the n is equal to 2 state. So it has a transition. If the photon emitted has a wavelength of 434 nanometers, what is the value of n initial? Right? What's going on here is that we're starting at some kind of n initial that we don't know what it is, and the electron is going down to the final level. N final is equal to 2. So this is what we're solving for. We could even call this x. N initial is x, okay? Because when the electron drops from a high energy level to a low energy level, it emits a photon that has a wavelength of, 434 nanometers. And they want you to solve for x. That's all they're asking you to do. Well, we know the formula that E, the change in energy, is equal to the Rydberg constant times 1 over n initial squared, subtract 1 over n final squared. We know the Rydberg constant. We know what n final is. We're solving for n initial, and we can calculate the energy from that wavelength, can't we? Because we know the energy is equal to hc over lambda. We looked at that this evening. So we have 6.63 times 10 to the negative 34 joules times seconds multiplied by the speed of light, 3.00 times 10 to the power of 8 meters per second, divided by the wavelength, which is 434 times 10 to the power of negative 9 meters, right? I just converted the nanometers into meters, 10 to the negative 9 meters. My units of meters cancel, as do seconds. I'm left over with my energy in joules. So my energy is going to be equal to 4.58 times 10 to the negative 19 joules. Now, it might seem like, okay, now I've got everything I need. I'm just going to plug this energy into here and I'm going to be done. Does anybody see what would be the problem if I just took this number and put it into this equation and I just started solving for n initial? Can anybody tell me what would be wrong with that, or where I might, what pitfall I would fall into there? Because I would be wrong. I would not get the right answer anyway. No? Okay. Well, this is emission, right? If it's going from a high energy level to a low energy level, this is emission. And if it's emission, delta E is going to be negative, right? We didn't put any negative numbers in here, but we know that this amount of energy was released, right? It was emitted. And so we're going to put a negative sign in front of that. Now we can start putting some numbers in. So we've got negative 4.58 times 10 to the negative 19 joules, which is equal to 2.18 times 10 to the negative 18 joules, multiplied by 1 over n initial squared, subtract 1 over, you guys can square 2 in your head, so 1 over 4, like that. Now we can simplify it. So we get 1 over n initial squared, subtract 0.25, is going to be equal to this number divided by this number, which gives you negative 0.210. Now I get 1 over n initial squared is equal to negative 0.210 plus 0.25, which equals 0.040 or 0.04. Then I get the n initial squared. N initial squared is going to be equal to 1 over 0.04. Take your calculator and take 0.04, take the reciprocal of it, and you get that n initial squared is equal to 25. So that means that n initial is going to be equal to the square root of 25. And that means that n initial is going to be equal to 5. There you go. So what are the keys from this question? You need to know that when you're dealing with emission, the change in energy is positive. I told you last time that when you're dealing with absorption, the change in energy is positive. So when we plug this delta E in here, we have to be sure that it's negative or we will not end up with the right answer. And the rest is just some algebra that you should be able to do. There we go. So that's a little bit of practice. And that really covers the practice problems that I had kind of, picked out from the first few sections of the book. And I picked out some other ones that deal with quantum numbers. And of course, we're going to do some more review on quantum numbers when we do the practice exam. I recommend taking a look at those problems. A real classic in chemistry with quantum numbers is trying to identify erroneous quantum numbers. That's a real classic in chemistry class. So anyhow,